So let's take a closer look at this word polymorphism, which we have come across earlier. So in object-oriented programming, as we have seen it so far, we use the word polymorphism to usually refer to what we normally achieve through what's called dynamic dispatch. So remember, the dynamic dispatch says that the function that an object executes depends on its runtime type and not on its declared or assigned type at compile time. So in particular, if you have two classes, so you have S, which is a subclass of T. So that means an object of type S can do everything that an object of type T can do and more. And in particular, if you have a variable of type T, right, you can assign it an object of type S. So wherever you expect a T, you are willing to take an S because S can do everything that T can do and more. Now T might define a function F, right? So T is here and it defines a function F, and S is a subtype and it defines an alternative implementation of F which overrides the method F in T. So S has a new implementation of F. So now, as we said, if you have a declaration of this type, capital T V, which says that V is of type T, I can now make this point to an object of type S, right? So I can assign V an object of type S, and now when I call F on this object, the question is which F are we going to use, because there is a compile time F which is associated with the type of V, and there is an object here who's of type capital S, and so it has its own more specialized definition of F. And what dynamic dispatch says is that the runtime value is the one that's chosen. So in this particular case, because the object itself, its identity at runtime is of type S and not T, you will use the function of F which comes with S and not with T. Right? So this is useful when we have a kind of heterogeneous mix. So remember the original Simula example where we had a queue of events and we wanted to associate with each event a simulate event action. So when we pick up an event from this queue and we say simulate, it knows how to simulate itself. So we don't have to say if it is of this type, do this, if it is of that type. So we avoid this kind of elaborate if-else case structure to try to distinguish the type and choose the appropriate function to invoke on it. Rather, we assume that these are all somehow compatible types. They are bound together by having a common supertype, and each of them has this function simulate, and therefore if I say e.simulate, then it will work regardless of what type of E it is, right? So every object knows what it needs to do, right? So it, based on its dynamic identity, it will appropriately behave. So we can have this array or list or queue of objects of compatible but different types and just invoke the same function on each of them, and each of them will know what to do. So this is a very limited view of polymorphism, which is associated with having one type overriding the function of another type. Now, normally in programming languages, right, polymorphism is more general than this, and it's talking about behaviors that require only specific capabilities. So we have already seen this in a sense in sorting, but let's look at three examples, right? The first is, supposing I have an array or a list of objects and I want to reverse it. Right? Now clearly what we are saying is that this reversing a list or reversing an array is something to do with the positions of the elements. It doesn't depend on the elements themselves, right? So if I put you in a room with a bunch of boxes and I say reverse the order of the boxes, you don't need to know what's inside the box. So that's a good way of thinking about polymorphism. I have some boxes, and do I need to look inside the box? To what extent do I need to look inside the box, right? So this is one example. I need to take a list or a sequence of values and reverse them. Slightly different is one which we saw before, a kind of find function which takes a sequence, an array of objects, and searches for one object and the other. Okay? And the third one is one where we actually want to arrange this array or list in a particular order based on some quantity. So now in all of these cases, right, there is a limited amount of information that we need about the objects in order to do this. So this is sometimes, if you want to distinguish it from this inheritance polymorphism as we find in object-oriented programming, because there is this confusion in programming languages about what polymorphism refers to, because the two communities of typically of functional programming types and object-oriented programming types use it in different ways. So far what we have seen is this inheritance type of polymorphism which comes from this class hierarchy. What we're talking about here is a more functional aspect, right? We want to do something with some objects. What do we need to know about them? So this is sometimes called structural polymorphism, just to distinguish it, right? So if somebody just says polymorphism, you need to be clear which one of them they're talking about, because unfortunately it's an ambiguous term. So as we said, if I just want to reverse the positions of objects in a list, right? Imagine you're in this room with a bunch of cartons and you're just asked to rearrange them in the opposite order. You don't need to open the cartons, right? So this should work for any type. How about this one, searching for an element in an array or a list? Again, this seems that it should work for any type, right? So if I give you a bunch of objects and I ask you to search for something, it should work for any type of objects. But there is a small subtlety, because I need to be able to check whether or not the object I'm looking for is in that array, right? So there is something which is implicit, which we need to make explicit, which is we need to be able to compare the object we have in our hand with the ones there. For example, if I give you an empty carton and I ask you whether it is the same as one of the cartons in the room, now I have to specify what I mean by is the same, right? Is the external appearance of the carton the same? That you can certainly check. But if I want you to check the insides of the carton, then you will have to open the carton. So you need more than just the object itself, right? So you need an equality check. So this requires some extra capability, right? And of course, sorting we have already seen before. In order to sort something, you need to be able to compare two elements and decide which one is smaller, which one is bigger. So you need a comparison function, not just whether one is equal to the other or not. So just to emphasize why this equality check is not trivial, right? Imagine that you have some capability of having functions in a list. So I could have a list of sort functions. I can have quick sort, I can have merge sort, I can have selection sort, and now I ask you whether a given piece of code that I have written is one of these. Now how would you check that, right? You would now have to check whether a function that I have written is the same as the function which is there in that list. Now it could be rewritten in a different format, so the algorithm could be the same, it could be identical. So of course if it is textually identical, it's easy, but if it's written in a different way, maybe with different variables and different indentation, then it becomes a problem. And if you want functional equality, then of course all the sorting algorithms up to a certain thing are correct. Correct sorting algorithms are all the same, they all sort. But the functional dependency could depend on the speed. So this notion of equality, I just want to emphasize, is not something which is obvious, right? It might be straightforward for values which have a kind of simple type, but if they are objects or if they are more complicated things, then the notion of equality may not even make sense. In fact, one of the fundamental results, as we talked about computing, is that when we talked about, for example, type checking and all that, is we cannot check if two programs are equal, if they do the same thing, right? So therefore, equality at the level of programs is something we certainly cannot do. So if we are trying to use Java to implement this notion of structural polymorphism, then what we have seen is that we can use this Java class hierarchy, use the fact that object is a kind of generic super type of everything. So we have this tree-like structure of all classes, and at the top we have this object class, right? So object is ancestor of every class that we could possibly use in any Java program. So with this, we can now write this first example, reverse, in this polymorphic way by just saying that we take, for reverse takes as argument an array of objects, right? Any kind of object, it doesn't matter what they are, and then this is just a simple reverse function. All it needs to know is the length, right? So once you have the length, then you start with the 0th element and the n-1th element and you swap them, right? So this is just a swap. It is just swapping I and n-1 minus I, right? It's swapping the ith element from the left with the ith element from the right. So the first element 0 is swapped with the n-1th element, second element 1 is swapped with the n-2th element, and so on, and you go until the midpoint. So either you have an odd number of elements, in which case you swap the two on the other side, or you have an even number of elements, in which case you go up to the midpoint and you swap the two which are either side of the midpoint. So that's what this I from 0 to less than n by 2 is doing, right? So it's a very straightforward thing, and all of this, right, just swapping the position at I and n-1 minus I does not require me to know anything more about the object except to just move these things around within the array. So this is easy to implement using this object idea. So anything that I pass will be compatible with objects. So that's the idea of this Java class hierarchy, because we know that a super type can take a subtype object as a concrete assignment, and we use that. So if we use find, it looks similar, right? We have seen this one before. we take an array of objects and we look for a specific object O. But what is kind of hidden under the carpet and which we are now making explicit is that there is something that we need to know about these objects. I need to be able to take the object at position I in my array and compare it to check whether it is equal to the object I'm looking for. Right? So this equal to looks very harmless, but as we just discussed, this may not always happen. Right? There may not be a sensible way to actually compare two objects, but fortunately for us, Java has defined an equals method in the superclass object, right? In this tree root class. So therefore, whenever I see equal to, if I have not made any other kind of sensible way of comparing objects, then by default it will check for what Java essentially thinks of as object equality. Are they the same location in memory? So equal to in some sense becomes a trivial check. Is it exactly the same object, same physical object, you might think? I mean, are they actually the same? Now, of course, in reality, this would never happen, right? If I give you a box and I ask you to check if a similar box is in the thing, they are not the same object. You have two copies of the object and you want to check if they are the same. That's the more realistic situation. But then hopefully you have written a method equals which compares them. Like two dates can be compared if the day, month and year are the same. But whichever you do, if you don't do anything also, the equality always holds. So just using object is good enough for us. The third example is sorting, and now we have a problem because we cannot necessarily assume that two objects can be sorted. So here our solution was to use an interface. So the precise requirement that we have for structural polymorphism is to allow something to be done if I have enough capabilities to do it. So if I want to now use quicksort on an array, then I want all the elements in the array to be comparable. So comparable now is something which is promised by this interface, and it has a function called CMP which allows me to compare two values by doing O1.CMP O2. So now I can use AI.CMP AJ and compare. Right? So this is more in line with really what we mean by structural polymorphism. We are actually exposing a capability of the object through some limited kind of window, and we are ensuring that any object which has that capability is sortable. So let's look at a slightly more complex example than find. Supposing I want to take one array and copy it into another array, right? So I have an array copy function which takes a source array and a target array, right? So in general, these two may not have the same size. So what I do is I copy as many as are there in the smaller array. So I first compute the minimum of the two lengths, the source length and the target length, right? And now for every I from 0 to limit -1, I copy from source I into target I, right? So this now becomes, in this Java sense, a polymorphic array copy. But the problem is, at runtime, I might try something like this. I might create an array of dates, and of the same length, I create an array of employees. And now these are two completely incompatible types, right? Date has got some kind of structure and it is somewhere in the hierarchy, and employee is somewhere else. They have no relationship to each other. But both of them, because of this Java hierarchy, date and employee are both compatible with object, right? So I can pass either of these arrays the way Java has set it up. If I have a subtype, then an array of the subtype is also an array of the supertype. So an array of date is compatible with an array of object, an array of employee is compatible with an array of object. So I can now say copy the date array into the employee array. And this of course would mean that at an individual level, I will have to take a value whose type is declared to be employee and associate it with a variable of type employee and associated value of type date, which is not allowed, right? So this will give me a runtime error. So this is a type error. I'm doing a type incorrect assignment, but I'm not able to tell, because inside this code, the fact that everything is an object hides the fact that this assignment here could be incompatible. So I only find out at runtime, and this is generally a bad thing. Any type error should be flagged at compile time. Now, more generally, right, it's not enough to just say that these must be the same type. It's not necessary that both are date or both are employee. For instance, we could have one type which is a subtype of another. We could have a class, say, which holds information about tickets, And then we could have a subtype called e-ticket, which holds something about electronic tickets, which might hold extra information like what IP address it was booked from and so on. So now everywhere where I see a ticket, I can also use an e-ticket. So if I'm copying from an e-ticket array into a ticket array, it's okay, because on the right hand side, right, the target value is expecting a ticket and it is getting an e-ticket. And everywhere where I expect a ticket, I'm okay with an e-ticket. So this is allowed. On the other hand, if I reverse this, right, and if I try to copy the ticket array into the e-ticket array, now this is a problem, because everywhere I expect an e-ticket, if I get something with lesser capabilities, namely the super type of ticket, this is wrong. So again, I have to distinguish between these two and somehow capture the fact that there is some constraint on this, right? So the earlier case, the constraint was that these two must actually be equal types. I said I want them both to be date or both to be employee, but more generally I want that the source type is a subtype of the target type. And that it's not clear how one can do when we use this object kind of notation in order to capture this structural polymorphism. Related to this is the data structure as a whole, right? So when we have a data structure as a whole, like an array or a list, what is important is the structure of the data, right? We are collecting together this data in a sequence, but now whether that sequence contains dates or employees or so on, many of the operations that we perform like reversing and sorting will not depend on the specific objects, but on the capabilities of those objects, right? So we should allow arbitrary types to be defined inside a data structure. So especially if we have a user defined data structure, like we have a list, right? So then again, using this mechanism available to us through objects. So supposing we want a generic linked list which uses a class node to store individual values, then the strategy is to make the data object stored inside each node and of type capital O object, which is this Java root class. And so whenever we return the first element in this list, it will return something of type object, and whenever we add something to the list, it will take something of type object. So this is similar to our earlier functions like find and reverse and so on. So we are using the fact that object is compatible with any value to ensure that this linked list can hold arbitrary values, because the nodes inside can hold arbitrary values. So there are two problems with this. So the first is that we have a type loss problem. So supposing I want to actually create a specific list which holds tickets, right? So I want to create a new list of this type, and I create two ticket variables. Remember, we had this ticket class that we talked about. So I create T1, which is a new ticket, and I insert it into the list, right? So since ticket is compatible with object, right, this insert will work. Now I want to take that object that is there in the list, the head of the list, and assign it to T2, right? So I want to take this value that head gives and assign it to T2. So I take list.head, but unfortunately if I take list.head, it comes out as an object. And I have on the left hand side a variable of type ticket which is more specific than object, right? It's a subtype of object with everything in subtype of object. But now I cannot expect, I expect something minimally with the capabilities of a ticket. I'm not able to handle an object. So I have to actually cast it. So each time I return this generic object from this list, I have to cast it to the specific type, which is a nuisance. The other more serious problem is that typically when we have a situation like this, we have a kind of a sequence of values or an array or anything, we do expect that across this sequence all the values are compatible, right? So we want a homogeneous kind of list. So now again we can do this following thing, that is we can create a ticket and create a date and insert first the ticket and then the date. So we can mix up the objects inside this because everything is going to be compatible with this parameter type object. So we need not have at the end of this operation, we cannot enforce in some sense that this list or array has a uniform type. So again we are limited. It's similar to what we said before about the functions which say like array copy, which wanted to check some compatibility with the source array and the target array. So here we want to check some compatibility between one object in the list and another object. We want to make sure that all the objects in the list are actually of the same type. So these are some shortcomings which were there originally in the language Java, and initially it was thought that this object-based hierarchy can solve all the problems which one wanted to associate with the structural polymorphism, but these kind of drawbacks became evident. So somewhere a few years down the line, Java added something which it called generic programming. So the idea in generic programming is that you add a new class of syntax called a type parameter. So for instance, if you want to say that a linear list that we have defined can hold an arbitrary value, but that value has a fixed type, then we'll say that it's a linear list of type T, right? So we associate with this linear list a type value T, and so for example, inside that list, if we see a function like head, then it must return an object of the same type as the type that the list was created with, right? So there is a way of now matching up what the functions do inside the class with what the class was created with. So instead of using object everywhere and all objects being independently compatible with any arbitrary type, here you say that I create it with a particular type, then the head will return a value of that same type, insert will expect another value of the same type, and so on, right? So we have these type parameters, and now we also had this problem of different types with some compatibility constraints. So remember, we said that in an array type, the source and the target could be of two different types. I could have two different type variables s and t, but not every source can be copied to every target, but I can copy it if s is a subtype of t. So I can now say that this function involves two variables s and t, two different types, but there is a constraint that s extends t, right? So these are the ideas that Java introduced in its so-called generics. So we will look at that next and see exactly how that works.